We've explored the error bounding for a Taylor polynomial. In this video, we're just going to look at a few examples of how we might use that formula. Recall that if we write a function as the sum of the nth order Taylor polynomial plus some remainder of x, then that remainder is equal to the n plus first derivative of the function at some point c divided by n plus 1 factorial times x minus a to the n plus 1. The value of c falls somewhere between x and a, the center of our Taylor polynomial. So our goal then is to find a bound m for the n plus first derivative. Once we know what m is, then we know that the absolute value of the remainder is going to be less than or equal to m times the absolute value of x minus a to the n plus 1 all over n plus 1 factorial. Okay, in our first example, we are going to try to bound the error for an estimate of the natural log of 1.2 using a second order Taylor polynomial approximation for the function f of x equals ln of x centered at a equals 1. So we know that r sub 2 of x has to be equal to the third derivative of the function natural log of x at some value c divided by 3 factorial times x minus a to the third. In this case, if f of x equals ln of x, then our first derivative is 1 over x. Our second derivative is negative 1 over x squared, and our third derivative is going to be 2 over x cubed. Our a value is 1, so we can rewrite this as r sub 2 of x is going to equal 2 over c cubed over 3 factorial times x minus 1 to the third. Now, c is somewhere on the interval between 1 and 1.2 because we are trying to estimate natural log of 1.2. 2 over x cubed is a decreasing function on that interval, which means that the third derivative for all values of c has to be less than or equal to the third derivative at 1. The third derivative at 1 is 2. So now, using that as our m value, we know that our error has to be less than or equal to 2 over 3 factorial, or the absolute value of the error, is less than or equal to 2 over 3 factorial times the absolute value of 1.2 minus 1 to the third. So we see that that is less than or equal to 2/6 times, that should be an absolute value sign there, 0.2, which is 2/10 to the third. So that is 8 over 3,000, which is going to be equal to 0.0026 repeating. So our error is less than 3/1000ths. All right, let's try another one. Let's do a trigonometric function this time. So we're going to bound the error. We're going to estimate sine of 5 pi over 4 using a fourth order Taylor polynomial centered at pi. And let's see how much error we might generate in that. So f of x is equal to sine of x. Let's first make a list of our derivatives. The first derivative is the cosine of x. The second derivative is the negative sine of x. The third derivative is going to be negative cosine of x. The fourth derivative is positive sine of x, which makes the fifth derivative, the one we need since we're finding the error in a fourth degree polynomial, that's going to be cosine of x. So we know that the formula tells us that the error in the fourth degree polynomial is exactly equal to the fifth derivative at some point c over 5 factorial times x minus our a value here, in this case, is pi, to the fifth. We know that c is on our interval between pi and 5 pi over 4. But we also know that the fifth derivative, cosine of x, is always less than or equal to 1. So we can just use 1 as our m value. It's a very straightforward way to do this. So using that m, we then know that the absolute value of the error at, in particular, 5 pi over 4 is going to equal 1, or I'm sorry, be less than or equal to 1 over 5 factorial times 5 pi over 4 minus pi to the fifth. So that is less than or equal to pi over 4 to the fifth over 120. And an estimate of that number is 0.00249. So once again, we see our error is bounded by 0.003 or 3/1000ths. Let's take a look at an exponential now. So here we're going to bound our error in estimating the square root of e. We're going to use the function f of x equals e to the x over 2. We're going to center that approximation at a equals 0. So we'll be looking at f of 1 to get e to the 1/2. Okay, so we know that if f of x is equal to e to the x over 2, to find the error in a third degree Taylor polynomial, we have to get the fourth derivative. So our first derivative is 1/2 e to the x over 2. Our second derivative is 1/4 of e to the x over 2. Our third derivative is 1/8 of e to the x over 2. And our fourth derivative is going to be, that's 4, going to be 1/16 of e to the x over 2. And our error, R3 of x, is going to be less than or equal to than 1/16 of e to the c over 2 all over 4 factorial times x minus 0 to the fourth, since we're centered at 0. We know that c has to lie between 0 and our x value of 1 because we're finding R3 of 1. Well, on that interval, the fourth derivative is an increasing function, which means that this is less than or equal to f of 1, which is e to the 1/2. Now, it's a little bit silly to attempt to use e to the 1/2 as our m value because we are estimating e to the 1/2. So what I'm going to notice is that e to the 1/2 is for sure less than or equal to 2. 2 is a little bit bigger than the m value that we need, but it makes for a simpler calculation, so we're going to go ahead and use 2. 2 is the closest integer to the square root of e that we know of, so we don't want to go any bigger than that, but this way we can deal with an integer. So r sub 3 of 1 is going to be then, the absolute value of that is going to be less than or equal to 2 over 16 over 4 factorial times 1 minus 0 to the fourth, so that is less than or equal to 2 over 16 times 24, which is 384, so we get that this is less than 2 over 384, which is approximately equal to 0.005. So our error this time is bounded by 5/1000ths. And there's, again, a little bit of wiggle room in that because our estimate for m was slightly higher than we needed it to be, but this still gives us a reasonable error estimate. We're going to wrap up with one last approximation, or error bound for an approximation. This time we're going to do a rational function. So we're going to find the error in an approximation of 1 over 2.2 using the third degree Taylor polynomial for 1 over x centered at 2. So we'll start again with finding our derivatives. We're going to have to find up to the fourth derivative in order to do the third order Taylor polynomial. These should look pretty familiar because remember that the derivative of ln x, which we did earlier, was 1 over x, and then the sequence is going to be the same here. So we're going to get negative 1 over x squared for the first derivative. The second derivative will be positive 2 over x cubed. The third derivative will then be negative 6 over x to the fourth, and the fourth derivative will be positive 24 over x to the fifth. So our error estimate at x equals 2.2 with an a value of 2, our error estimate is going to be equal to f to the fourth of c over 4 factorial times 2.2 minus 2 to the fourth, where c lies in the interval between 2 and 2.2. But notice that the fourth derivative is a decreasing function. I know that because if I took the fifth derivative, it would be negative. So we know that f to the fourth of c has to be less than or equal to f to the fourth of 2, which is 24 over 2 to the fifth, which is 24 over 32, which is 3/4. So we're going to use 3/4 as our m value. So r to the fourth of 2.2 then, replacing f to the fourth of c with m, we get an inequality. So we're going to do this as 3/4 over 4 factorial times 2/10. That's 2.2 minus 2 to the fourth. Got a lot of fractions to deal with there. So that's 3 over 4 times 24 times 2 to the fourth is 16 over 10 to the fourth is 10,000. So I'm going to do some cancellation real quick here instead of getting out my calculator. And I see that my error is less than 1 over 20,000, which if you like decimals more than I do, you will see that that is 0.00005. So tiny little error estimate in this particular estimation. So summarizing once again what we've seen here, we know that if we can bound the n plus first derivative for our given function by some number n, then we know that our error estimate has to be less than or equal to that m times the absolute value of x minus a, where a is the center of the Taylor polynomial, raised to the n plus first power, all divided by n plus 1 factorial. The real challenge is figuring out what m is, but once you've got that done, the rest of it falls into place.